Good afternoon to you too, and good afternoon to everyone that we've got with us. I'm sure we'll have a few more stragglers coming through over the next couple of minutes, but we will kick things off. You're happy to take questions during the presentation. So if any of you do have questions, then please post them in the chat for Miroslava. And we can unmute you if need be. If you write them in, then we'll get them answered, and there'll be time at the end for questions as well. And if I could ask that everyone provide feedback, I will provide a link to give feedback, but it will also be on the slide. And just like to take the time to thank you all for attending, and thank you, Miroslava, for presenting, and I'll hand over to you.
All right, good afternoon, everyone. I'm happy to be here today. Today, I'm going to talk about a case study, a successful performance optimization that I applied in my clients. I am Miroslava Barona Rossi. I am from Brazil. I today work in Kindu, Canada, and I have about 23 years of experience in the IT industry and 15 years plus in performance and capacity analysis, mainframe performance and capacity. Okay, so the context of this presentation today is that clients fail to leverage the full potential of their mainframe platform, and often they underutilize their capabilities, the full potential of the mainframe. So today I'm going to share with you some of the techniques that I applied in my clients to optimize the mainframe utilization, either reduce CPU time per business transaction, improve transactions per second or throughput rate, CPU upgrade cost avoidance, how you can maximize the life of your asset, right? Reduction in batch processing wall times, and as I mentioned, an elongation of mainframe asset life. So it always starts with applying capacity planning best practices. Here I'm going to read just a little bit a piece of the large system performance reference regarding workload capacity performance, right? So workload capacity performance is sensitive to three major factors. One, memory hierarchy. Two, instruction path length. And three, instruction complexity. So I'm going through these concepts here that are key for capacity planning that are inside large system performance reference document that I strongly recommend for all capacity planners to read it. And then I'll point out a few tips or things that I look at in each area so you can maximize the use of your mainframe, okay? So basically, the memory hierarchy of a processor generally refers to the caches. Some of the caches are private to the microprocessor, which means only that microprocessor may access them. Other caches are shared by multiple microprocessors. So summarizing here, up to the Z15, we had L1 and L2 caches dedicated to the PU core, right? And L3, L4 in memory was considered the nest, okay? And on the Z16, we have for sure dedicated the L1 cache, and the L2 can be dedicated or can be semi-dedicated as it's mentioned in here in this slide. It was extracted from TLLB on the Z16, and L3, L4 and memory are the nest. So why does it matter to capacity planning? So imagine that if you or if the data that's being processed into the system is fetched from L2 and L2 and L1 and L2 cache or dedicated caches, they tend to spend less CPU cycles per instruction, right? Because they are closer to the PU. In the other hand, if the instructions that it's being processed, the data of the instructions that it's being processed, it's on the L3, L4 in memory or the nest, it tends to consume more CPU cycles per instruction. So let's leave this thought. Okay, so another point that we need to understand, hardware design defines how a processor can perform. Okay. So hardware design defines how a processor can perform. The software being exercised on this hardware determines how a processor actually does perform. So what does it mean? So basically, we have, for example, for bidding purposes or for commercial purposes, mainframe has like a MIPS table, right? Where you define or it's a baseline for the capacity of each mainframe hardware. Okay, but under LSPR, you have not only one table or only one value per mainframe hardware and processor model and type. You have more than one, let's say, capacity value for each of the processor model and type. And why is that? It's because it depends on the workload that you're running on this mainframe hardware, right? Depending on how this workload mix exercise in this hardware, or how much this workload mix go to the nest. Let me see how I can get rid of, okay, better. So it depends on how much the workload that you're running goes to the nest to actually execute the transactions or the batch workload, etc. If it tends to go or it tends to be nest intensity, then this workload classification under LSPR tend to be high, or you have less MIPS per processor or hardware, right? And if you have, for example, a workload that the workload mix is more batch related at certain points of the day, for example, during the night, etc., you tend to extract more capacity or more MIPS from the same hardware or from the same machine model and type. That's why it's so important to have the CPU MF records or the SMF 113 records available in collecting, because the 113 or CPU MF can give you a very good view on how your workload behaves with that processor model, okay? So in this example here, the purple area shows the low, the workload classification low in the LSPR table. The yellow is the average and the high. So, and the values here are, for example, the intervals, right? So in this case, in this particular LPAR, we can see that the majority of the workload is classified under average. So whenever I do, for example, a selection of a hardware or a mainframe machine type and model, I'll select this MIPS capacity table, let's say, to assume that my workload will have all of these MIPS or capacity available to the workload. Okay, it's a little bit complicated to explain, but in the summary of this slide is make sure you collect the SMF 113s and make sure you understand how your workload mix or the majority of your workload or the main workload during business critical hours is classified, so you don't make a mistake. For example, if you have your workload classified as high, have high transactional workload or high IO intensive, etc., and maybe one machine type and model that you're envisioning to buy, right, would not be the right fit, because the high workload tends to, you know, give less MIPS per mainframe processor model and type. Okay. Let's move on. Okay. So one of the key metrics out of the CPU MF is the cycles per instruction. Okay, so we talked about a little bit the relative nest intensity and how this is important to classify and understand your workload behavior. But there's a better metric, if you want to call it like that, to keep track, which is cycles per instructions, or CPI. So I'll give you an example of an analysis that I did here to improve the CPI And at the end of the day, if you decrease the CPI, you decrease the whole CPU utilization of the environment, okay? So what I did here in this particular case, this client was moving from a 500 engines. It was a I think Z14 520, and they are going to the Z15 708. So the other thing that we need to understand as well is the engine speed. So in the 500 engines, you have less MIPS per CP. In the 700 engines or full capacity, you have more MIPS per CP. Then how all this come into play? So basically, I wanted to see how much or what were the processor polarity or how much vertical high, median, and lows each LPAR had, right? And based on that, I compared or cross-checked it with the CPI metric here. So take into consideration this LPAR here, NAS3, it had 3 vertical highs, 1 vertical median, and 4 vertical lows. Whenever the batch workload was running during the early morning, the CPI used to jump up to the 3, right? And then it went back down to 2 or 1, and then at the end of the day, also use it to jump. So during these jumps on CPI, the usage of the vertical lows were intensive. And take into consideration that vertical high processor has a one-to-one relationship from physical to logical. That means that whenever the LPAR is processing the data, the probability to find the data into L1 and L2 cache is higher because you have the same work being dispatched on a logical CP that it's in the same physical CP at the end, the background. But whenever that happens, whenever an LPAR is processing work and you are in a high peak and in use of the vertical lows, that one-to-one relationship is not true anymore. So there is more probability that the data that's being processed would be fetched from L3 and 4 in cache, and therefore they will consume more cycles per instruction, like it's showing here in this graphic, right? So the exercise that I did to move or to migrate this processor from a 500 modules to a 700 modules, of course, I would lose a lot of this vertical high, especially for this production LPAR here. But in the other hand, I would optimize some significant amount of CPU. I would reduce the CPU cycles by removing all those extra vertical loads. Okay. So instructions path length. A transaction or job will need to execute a set of instructions to complete its task. These instructions are composed of various paths through the operational system, subsystems, and application. So basically, the total count of the instructions executed across the software components are the transaction or job path length. So what it has to do about optimization or capacity planning. Imagine that if you are in a system where it's busy or it's stressed, running at 100%, having all tasks competing for resources, those operational systems or subsystems executions will be higher, right? Therefore, will consume more CPU resources. So the more stressed, the more busy, the more the tasks are competing for resources, the cycles per instructions or the CPU span is higher, right? So it's not healthy or it's not very smart to run a CPU at 100% all the time. The other component here that we need to consider, the n-way number of logical processors. So as the number of the logical processors grows, more instructions are needed to serialize the work that it's being processed. So let's go through these two items and take the tips or the recommendations that I have here for you. So in terms of it's not good or it's not healthy to run a CPU at 100% all the time, use rules of thumb for capacity planning. It's fair, right? A general tip or rule of thumb that I use if I don't know, for example, if I'm starting to support a customer that I don't know exactly their workload, the first threshold or the rule of thumb that I use is 85% of CPU capacity at the monthly average at prime time, because normally at the prime time you have the business transactions, etc. For sure, there are exceptions, right? But I'm just giving you a threshold that I generally use. And also, of course, make sure you keep track of your peak days. So for example, month ends are normally the stressful days or for many of environments out there, right? Because you have batch month end and you have, for example, higher transactions, let's say a bank that it's always there's the payday in the beginning of the month, etc. So the first days of the month normally for a financial or, for example, for a bank are higher, right? So keep track, of course, of the peaks, but a general rule of thumb in a monthly average would be try to keep the utilization below the 85% in a monthly average, right? The other tip that I, of course, would like to recommend is project your CPU utilization, right? Can be a simple linear projection, or it can be a seasonal projection. Seasonal is the one that I like the most because all business have their up and downs, especially, let's say, for example, Black Friday is normally busy for clients that have stores and sell, etc. Or there are many types of business, but there's always a seasonality in there. And therefore, I'd recommend you to try a seasonal forecast as well. Keep track of the next upcoming upgrades, right? Because it's not cheap to, to get the approval or financial approval to do an upgrade. So by doing the CPU forecast, you will anticipate or you help the company to better plan for the expense, right? So the other good tip that I was going to talk about here, configure LPAR weights as per LPAR CPU demand. Sounds silly, but what happens is, for example, if you have an environment set up for, I don't know, 2 or 3 years, you at first did one nice analysis and did the setup of the LPAR weights carefully on the HMC, but as the time goes, the demand or the LPAR hungry for CPU might increase, right? So imagine that your LPAR or your system, you know, as the year goes by, it starts to consume more than before, or business purposes or for whatever purposes. So this chart here I use to evaluate if the weights are good enough or if I need to adjust, okay? So basically this is an hourly profile from 0 hour up to the 23 or 11. Then all of these lines here are a month. So how do I average those values per month? So take into consideration the month of February, for example, in the 0 hour. Sort the CPU utilization at the 0 hour from the highest to the lowest and average the 10 values. By doing that, you won't, for example, neglect the peak days that I mentioned, right? Month ends, first week of a bank transaction week, etc. You won't neglect, you won't bring all the average tends to get the value down. And by doing that, you you will be sure that will be take into consideration the highest CPU utilization days. And why in a 24-hour average? You know, it's very nice to see how your workload fluctuates along the hours. And as you can see, this is February, March, April, and May. They are pretty similar month by month. So whenever you see a change into the profile, you all in the month to the other, you might see, what changed here? What happened in this hour? So it's pretty interesting, this chart. I use it a lot, and I use it since forever, since I started working in performance and capacity. What else? So, okay, so this is the LPAR hourly profile utilization. This gray line here, or the black line here below, used to be the weight, the MIPS capacity, or the minimum MIPS capacity per their weight, okay? So what happened here? There was a huge, a very significant intervals, these hourly averages, that this LPAR were using above this weight, and this is not good. This is terrible for performance, because that means you're highly using, for example, vertical load processors. And as we mentioned before, vertical load processors tend to fetch the data from L3 and 4 cache, therefore spend more cycles, CPU cycles per instructions, right? So what would you do? You would increase this weight up to this yellow line, so you cover the main CPU utilization for this LPAR, or you satisfy this LPAR for hungry for CPU, okay? I had a little pizza here. So imagine, I like to explain to my mentees that imagine that the mainframe is a pizza, and all the slices are the processors. So break down, divide the capacity of this mainframe by the processors, and try to give the right slices to your LPAR. Okay, so the other key tip here that I'm going to mention is optimize logical to physical CPS ratio. So what that means, imagine that you have, I don't know, 10 processors, real processors or physical processors activated in your mainframe, and you have, I don't know, 20 LPARs. So this relationship between the logical CPs that are assigned to all LPARs back to the physical CPs are the ratio. The tip is to keep the logical to physical ratio under 3, right? Don't have, for example, like I was mentioning before, whenever you're going to do an upgrade change, take into consideration the processor speed. And if you have larger and fewer CPs and your logical physical ratio will get terrible or above 3, don't do it. It's best for you to, for example, consider the 600 modules or the 500 modules, right? It's very important. Oh, another tip here, use ZPCR tool to help you to calculate all that. See, for example, the minimum, the maximum capacity, or as per their weight. ZPCR also take into consideration the SMF113s or CPUMF records, and it will help you to classify, and you understand how many MIPS exactly you're extracting from your configuration. It also calculates for you the logical to physical ratio, and it has an optimization recommendation there for logical CPs. And if you decide to hit the button of have minimal logical CPs per as per their weight, it won't, for example, assign extra logical CPs to the LPAR or vertical loads to the LPAR. So that maximizes the use of your mainframe, and at the end of the day, reduce the CPU utilization or reduce the CPU cycles per instruction. It's a very important one. Okay, so At the end of this capacity planning best practices, here we have instructions complexity. Again, this was extracted from LSPR document that I recommend you to read it. So the type of instructions and the sequence in which they are executed will interact with the design of a microprocessor to affect a performance component we can define as instruction complexity. So basically, how first that translates to our reality. You see an environment over decades going from machine model and type, from machine model type, and many times the application that it's running on this very modern mainframe processor are not taking the full advantage of the new instructions that are available. Make sure whenever you do an upgrade, also work with your application teams to leverage the new instructions available, right? Because they are more optimized, they tend to spend less CPU or less cycles per instruction. Okay, so all the tips that I gave here was to optimize your mainframe based on capacity planning methods, right? So here it's a little bit more outside of the capacity planning best practice, but into the performance, okay? CICS thread safe. It's a very interesting and very good capability here from CICS. The majority of the clients or the majority of the environments out there heavily use CICS, right? And one interesting method of optimize the CPU cycles per transaction is to evaluate, of course, if you apply CICS thread safe, you will parallelize or you execute transactions in parallel, and not all the applications are eligible to that type of parallelism. Okay, so make sure you engage your application team, your CICS specialist, but if the transaction or the main transaction are eligible for thread safe, go for it. The numbers that I have in experience in the accounts that I worked was 25% of CPU reduction per transaction. It's huge. Okay, so outside from the CICS point of view, I just wanted to give you a little bit of some tips or what a decent workload manager policy review will have. A decent workload manager policy review will have the following best practices applied. And when we do, these are the main results. So here are some tips that I implemented in my accounts. So normally workload manager as HMC, the workload manager policy, it's not reviewed very often, right? And when I say that, it's like decades of not having any review or adjustment in goals. And that is a huge opportunity for clients or for environments to do performance tuning, and also reduction or elongation of the mainframe asset life. Because if you have a well-tuned workload manager policy, you can run hotter, right? You can run at 100% without impacting, for example, your business critical transaction or application. You maximize the use of your mainframe, okay? So here are some tips. Normally we have many service goals and service classes and periods in the installation. So this is not recommended. Try to keep the number of service classes and / periods under 25 or 30. More than that is too much. I'm sure you're not using, or you're just adding overhead to your WLM policy. Also, the excess of WLM policies. I have seen, for example, installations that had many policies for each specific situation. So instead of the client to let the WLM to decide whenever to change the dispatching priorities. This client, for example, here, it used to use automation to change the policy, and all of a sudden implement a resource group with some other value. Resource groups caps a workload, right? So if you change workload policy to change resource group values all the time, during this change, what used to happen here, CICS used to, during these changes, CICS transactions used to fill, and dispatching priority were not well classified or assigned to the CICS business critical transactions. And at the end, you had CICS micro incidents, right? It had delay, etc. So try to not do that, right? Let the WLM is smart, and it's getting smarter, especially on the 3.1 or the ZOS 3 versions. Let WLM decide, and do not try to over or do an excess of use of many WLM policies. The other common error here, for example, some environments or some clients like to segregate a lot the service class and period. So I'll give you an example. This service class will be for CICS transactions, debit transactions. So this CICS service class will be for credit transactions. These will be for, I don't know, long running, or they assign many service classes with less or 15 differential points, less than 15 differential points, one from each other, for example, in the velocities, or the response time goals are pretty similar. This is not good for WLM. WLM tends to, I'll say, get confused. Then it's not good for at the result at the end of the day, it's not good. So try to consolidate as much as possible. And if you want to segregate, for example, for better controlling or for better reporting, try to use report class instead, right? Not service classes. Okay, it's a common mistake as well. Excess of CPU critical flag, this is not good as well, because every time their WLM will ensure this CPU critical flag, it's an extra action that they do each cycle, right? So WLM is constantly doing checkouts every 10 seconds. And whenever the service class has CPU critical flag, WLM goes and ensures the dispatching priority every time. So let WLM decide whenever it has to increase or reduce the dispatching priority, right? And remove the excess of CPU critical flags. This is a good one. Turn off WLM priority management. So in the beginning of the WLM policy, you have there, if you want to set up priority management to yes or no, make it no. We had a huge enhancement here when we did that in this, for example, in this case, up to 50% of reduction in CPU delay when we did that for the service classes that the main service class or the main CICS service class. That was huge decrease in CPU delay. Of course, start the WLM review by doing that, because at the end of the day, whenever you do that, the velocities will never reach, for example, higher numbers as they used to be before, right? So start by doing that and then adjust the whole policy accordingly. Another good one is maybe you see, for example, some environments or some WLM policies where you have many batch service classes and some of them with very high importance. That's not good. Try to dedicate the importance 1, 2 to online workload. So no, not all your workloads are priority 1. I understand your batch is important. It produces a report to the CEO, etc. but the online workload needs quicker access to CPU, right? And so try to dedicate importance 1 or 2 for online workloads, and 3, 4, and 5, 3 for hot batch, and 4 and 5 to the majority of the other batch. That will keep your online safe and your workload mix, everything will run smoothly. So at the end of the day, for example, in this specific case here, in a Kyndryl zCloud Brazil client, the client came into the cloud with a policy with many room for opportunity. Once we finish the WLM review, the performance and capacity team was not engaged anymore in any critical instance. Before, it used to be like every day, all night, all day, all night, micromanaging the environment, changing policies, changing resource groups, changing, dealing with CICS micro instance, etc. So there's a lot of benefit to have a well-tuned WLM policy. So this is the summary of the main results. Elimination of systems overhead, right? Elimination of CICS micro instance, as I mentioned a few times. Elimination of manual interventions, we're prioritizing jobs, etc. So you stop the micromanaging. Batch workload not impacting CICS transactions. We had a situation every day at 8 p.m. where the batch used to kick in and CICS transactions fell, and the dispatching priority was not high enough for CICS transactions because batch had a very high importance. So this is not good. Elimination of create seats, instant calls, etc. There are many benefits by doing a workload manager review policy. So these are 2 interesting charts that I wanted to share with you. This one, for example, in this environment that I was mentioning, that we did all of these actions, the green bars here are transaction counts, CICS transaction counts growing, while the CPU utilization was decreasing. So this is huge. This maximize or optimize your mainframe, right? And this was the 15% reduction in CPU delay whenever we turned off their IO priority management. So this was huge as well. So thank you. I'd like to see if there is any questions, comments. I'm sorry about my English. I'm Brazilian, but I did my best here.
Thank you, Miroslava. Your English was excellent. No need for that. But yes, does anyone have any questions? And whilst people are thinking of any or typing them up, I'd just like to draw everyone's attention to the link in the group chat that allows you to give us feedback. It's very helpful when, when we're organising the conference, we do use the feedback, and you can also use the QR code on screen. I would also ask Miroslava if you could put your email address in the group chat. That way, if anybody thinks of a question or two after this has ended, then they can follow up with you directly.
For sure.
Thank you.
Thank you so much for your attendance.
No, thank you. I mean, it doesn't seem that we have any questions, so we will end the session there. I'd just like to thank you again. It was an excellent session, and again, if people could provide feedback and email you any questions afterwards. But thank you. We'll end the session there, and thank you very much, Miroslava.
Thank you. Take care. Bye.
Bye, everyone.